Until now, we have considered only discontinuous systems, that is, systems with two regions, 1 and 2, within which we have had a transfer of matter, energy, or charge between the two systems, but they were discrete systems. Now we're going to look at continuous systems, systems which don't have discrete boundaries but have continuous variation from one side to another. So in this case, our intensive variables will not only be a function of time, but they will also have a dependence on the space coordinates. That is, they are continuous systems. An example is a metal bar heated at one end and cooled at the other. We have a continuous range of temperature between the hot side and the cold side. Another example is a mixture of diffusing components. So this case is the more realistic case. We are not talking about discrete systems anymore, but continuous systems. To describe these continuous systems, we do not need any new physical principles. We only need the continuity equation, or for example, in the case of matter, the conservation of mass. So this equation 66 is the continuity equation, or the variation of the mass density in time, which is just equal to minus the divergence of the mass density times the velocity of the flow of the matter coming into or out of the system. So this equation 66 might look a little bit mysterious, but in fact it comes from Gauss's law, in which the change or the rate of change of a variable of a system within a well-defined volume with a given surface is just equal to the flow, the normal component of the flow, integrated over that surface, or using Gauss's law, just equal to minus the divergence of the flow over the volume that that surface is bounding. So this equation 66 is just the equation of continuity for the mass density rho, and where omega, as a vector, is the macroscopic velocity of the material which is moving in the system. And I will remind you that divergence is just given by this mathematical formula, which is 67, equation 67. Now, equation 66, the continuity equation, also holds for a mixture of different components. So, in this case, omega then refers to the velocity of the center of gravity, which is just defined as omega is equal to the sum over all the components in the system of the densities, the mass densities of those components, times the velocity of the flow of those components over the total density rho. In general, the local change of a physical quantity is due not only to the divergence of a current, but also to a source term. For example, if we consider a chemical reaction in which we are producing certain components, gamma, the equation of continuity for the mass density, rho gamma, that is of the mass density of component gamma, is just this equation 69, in which we have included the second term, which are due to the production of that component gamma due to the chemical reactions. And we can see that if we go back to equation 1.1 of the book of Prigogine, where dm gamma is just equal to the stoichiometric coefficient of gamma times the molar mass of substance gamma times d chi, which is, remember, chi is the advancement of the reaction. So d chi by dt is the velocity of the reaction. Or in other words, the rate of the chemical reaction per unit volume. Now we have to talk about all substances per unit volume, because now we are considering the continuous and not a discrete case. For any component gamma in the system, the flow can be decomposed into a flow with respect to the center of mass of the system, and the diffusion with respect to the flow relative to the center of mass velocity. So for example, we can write rho gamma, omega gamma, is equal to rho gamma times omega. Omega, remember, is the center of mass velocity of the system, plus rho gamma times the difference of the velocity of the component gamma with respect to the velocity of the center of mass of the system. So here in this equation 70, delta refers to the diffusion velocity with respect to the center of mass of the velocity of the system. And note that by our definition, equation 70 of the diffusion velocity with respect to the center of mass velocity, we know that the sum over all components of their densities times their diffusion velocity with respect to the center of mass of the system has to be equal to 0. So not only for the mass density, but for every extensive variable, we can write an equation very similar to equation 69. For example, for the entropy per unit volume, we have a term which is equal to the divergence plus another term, sigma, which is equal to the production. The divergence is the flow of entropy over the boundary of the system, and sigma is the production due to irreversible processes occurring inside the system. So equation 72 is just an extension of the change of entropy being equal to the change of entropy due to the flows of entropy coming in from the outside, the external environment, or going out to the external environment, plus another term which is due to the internal entropy production of the system. So this equation ds equal to des plus dis is just exactly equation 72, but for the case of a discrete system, which we treated before. Now we're going to treat continuous systems, so we will have to use equation 72, which includes a divergence of the flow, the entropy in this case, plus another term, sigma, which is equal to the entropy production due to irreversible processes. And note that for reversible processes, the production of entropy is equal to 0, sigma is equal to 0, while for all irreversible processes occurring within the system, the entropy production has to be positive definite. Sigma is greater than 0, equation 73. So now let's calculate again the entropy production due to a system composed of two parts, 1 and 2. Okay, so this is the discrete case in which parts 1 and 2, or regions 1 and 2, are open to each other, so we allow a flow of energy and matter from subsystem 1 into subsystem 2, and vice versa. And the system 1 plus 2 is closed as a whole, so we only allow a flow of energy over the boundary of the system, the complete system 1 plus 2, but we don't allow flow of matter over the whole system. So now if you remember, this is the form that we derived for the entropy production for this system. And you can go back to equation 56 to see that. So the entropy production, internal entropy production, is just due to one term, which is the force, 1 over P1 minus 1 over P2, times the flow, in this case was the flow of heat, plus the flow of energy, which is coming in from the matter, because we're allowing matter to flow between subsystem 1 and subsystem 2. So the first term here was the production of entropy due to the flow of energy. The second term is the production of entropy due to the flow of mass, where the mu gammas are just the chemical potentials of the component gamma in system 1 and system 2 over their temperatures, times the flow of the material of that substance gamma. And the last two terms are due to the chemical reactions which are occurring inside system 1 and system 2. So there the force for the chemical reactions was just the affinity over the temperature, A over T, and the flow was the velocity or the rate of the reaction, V, rate of the chemical reaction. So now, rather than a discrete system, we assume that we have a continuous system. And we ask how equation 74 would look in the case of a continuous system. We won't derive it here, but you can try to derive it for yourself. Equation 75 is the corresponding continuous case for equation 74 for this system that we have of system being open to flow of material and energy inside that flows on its boundary and only allowing a flow of energy over the boundary. So the first term here is W I with the superindex I represents the flow of heat in the coordinate I. So this I is the sum over 3 coordinates x, y, and z of the system. And it is multiplied by a term partial T, the temperature, with respect to x, the x coordinate. No, it can be x, y, or z, that's why subindice I appears there, over the temperature squared. That first term corresponds to the first term in equation 74 for the flow of heat, flow of energy through the system. Now the entropy production due to the flow of matter in the system, in this continuous system, is just this second component of the equation 75, second term, which is the sum over all of the components gamma in the system, which are diffusing, this is the diffusion term, times a sum over all of the indices x, y, z coordinate space. And F here, this F is the force, the external force. We're allowing, in this case, an external force to exist over the system. For example, an electrical potential, which would provide a force if the components were charged in the system. And this minus T times the partial mu. Now here mu plus, with this superindice plus, is the chemical potential per unit mass. Because now we are looking at the volume, regional volume, so we have to do it per unit mass over the temperature with respect to partial x, y, and z. And it's multiplied by the mass density times, now this delta, remember, is the velocity of component gamma with respect to the velocity of the center of mass of the system. And in each of its 3 components, x, y, and z, that's why the subindice I again. And then we just have a single term for the chemical reactions which are occurring in the system, which is the affinity over the temperature times the rate of the reaction, V. And now by the local formulation of the second law of thermodynamics, this entropy production has to be positive definite. So here we're not going to derive equation 75. It should be fairly obvious that it is the correspondence of equation 74, but for the continuous case instead of the discrete case. Now in the present description of continuous systems, we must distinguish between the bulk movement with velocity omega, remember omega is the velocity of the center of mass of the system, and the c, this is the number c, which is the number of different components in the system, the fusions of these different components with respect to that of the center of mass. So there are only really c minus 1 linearly independent variables delta gamma. Now also note that we are considering non-viscous systems, that is, no friction with respect to the outside. So the flow of the center of mass does not appear in the equation for the entropy production. the entropy production is only due to the flows with respect of the flows of the different components with respect to the velocity of the center of mass of the system. So now let's consider a simple example of a continuous system. In this example, we only allow two components. We have only component 1, gamma equal to 1, and gamma equal to 2. So we have only the fusion of matter. But we allow forces over the system, so we can have an electrical potential over this system, for example. And we would have a different force, F1, for component 1, and F2 for component 2, because they could have different charge, for example, if it was the force due to an electrical potential over the system. But we assume that we have no temperature gradient, so we have no flow of heat in the system, and that we also do not have any chemical reactions occurring within the system. So this is the case of only the fusion of component 1 with respect to component 2 for the case of a continuous system. And we'll see that equation 75 reduces to this more simple equation 76 for the entropy production for that diffusing system with only two components. Note that in this equation in this equation 76, we are assuming that the forces F1 and F2 and the gradients of the chemical potentials are only acting over the x distance, the x coordinate. That's why we don't have a sum over I, sum over x, y, and z, because we're assuming it's only to be a one-dimensional system. Note that instead of using the average mass velocity omega, we could have used any reference velocity. For example, if we had chosen velocity omega 2, then the entropy production becomes this equation, which is equation 78. And we can show that this remains invariant, the entropy production remains invariant with respect to what velocity is chosen to measure the diffusion with respect to. And you can show that equation 78 is the correct equation. And you can do that by using equation 71. Sum over all components gamma of both gamma times delta gamma has to be equal to 0.